مرحبا طلاب. راح اليوم بعد ما خلصت شابتر 4 راح أحل لكم كم من سؤال على الشابتر حتى تصير واعذروني مش بحل يعني on the spot لأنه it would take a long time and so I'll start with the question 12 and he's giving us a circuit. He wants the transfer function. He's taking the output here, from here to here. This is VC, okay? This is the output at the capacitor. And from this transfer function, after you substitute the value which is given to us, like I put here R1, R2, L, and C, and then we'll find the transfer function, and from the transfer function he wants us to state whether the system is underdamped, overdamped, and critically damped. Of course, we took modeling and simulation in chapter 2, so now maybe we can make use of this model which we use in chapter 2. So here, first of all, you put in Laplace transform. So I'll put the Laplace transform of the circuit. Okay, I'll put it here. So I'll transfer this circuit into this one. This is the Laplace transform of the circuit. So this is R1, this is U of S, this is the input, and this is R2, this is the same. This is LS, this is 1 over CS, and this is VC of S, of course. And I'll take a node method because as you see, all these are parallel. So I have only one node. All this is the same node. Okay, so it will be easier than if you take meshes. No meshes here, okay? We'll write the node equation. So we said V minus U over R1. These are Kirchhoff current law, of course, Kirchhoff current law. So I'll say V minus U over R1 plus V over R2 plus V over LS plus V over 1 CSS. So I will have this equation. Okay, I hope it's clear for you. Now all is left is put everything related to V. V is VC. Related to V on one side, and put U, which is the input, on the left side. So I'll have U over R1, and so it's V, I'll say it, the transfer function V over U equal 1 over R1 over whatever I have in here, okay? So I'll have VC of S over U of S equal 1 over R1 over 1 over R1 plus 1 over R2 plus 1 over LS plus C of S. Substitute for this value which is given me before, R1, R2, L, and C. And let's say simplify. We'll get the transfer function. This is S, 10S. This is S, 10S. Okay? 10S, VC of S over U of S equal 10S over S squared plus 20S plus 500. If we're talking about, we'll consider that we take the denominator. We said that we only take the denominator if we don't have this. But this is our characteristic equation. From the characteristic equation, we see that the roots are minus 10 plus minus J20, which are complex, which means that the system is underdamped. So when you look at it, it will become easy once you know how to tackle the problem, okay? I'll continue with the question so that I'll go further. It's not required, the question and the solution is finished here, but I'll continue with as long as we are here, so I'll do the transient response for you, okay? So what did I do? I assume we need to find the step response as if it's required. Let's say this is an exam question, let's say, and we are required to find the step response. We found that VC of S equal 10S over S squared plus 20S plus 500 U of S. He wanted us to find VC of T for U of S equal 1 over S. Now this is a different situation, and that's why I am solving solving it for you. So VC of S, it will be, we'll have this will cancel with the step, and you will have this. This is an impulse. This will be an impulse response because it have a 10 over this without the S. This S is disappeared because it's cancelled with this S I have in the numerator. So if we look in the, we can use the expression we have. You remember I gave you for underdamped for a step response, but here we have an impulse. Here as if you have an impulse. When you have an impulse response for a system like that, the transfer function will be similar to this, okay? If we look into the Laplace transform, I'll show you. I have the Laplace transform table here with me. We'll use the Laplace transform. Even this one, if you remember, if we have omega n square, which I gave you before, and we have this, this is the expression which I gave you, 1 minus 1 over this is beta. I hope this is clear. E2 minus this, he's using sine plus phi, and I use cosine minus phi, so it's the same. And this is phi equal tan inverse beta ala zeta because he swapped it, he used the sine. Now we're going to use, this is the transfer function we have. We have omega n square. Let's assume we have to arrange it that we have omega n square over s square plus 2 zeta omega n vs times omega n square. The Laplace transform will be that one. So we use number 22. You know that in exam we'll give you this Laplace transform table. So we'll use that one. And I'll put it on the on my sheet. So we use, if we have f of s equal to omega n square over s square plus 2 zeta omega n vs plus omega n square, then f of t, this is I took from the Laplace transform table. F of t will be like that, omega n over, this is beta, e2 minus zeta omega n t sine omega n times 1 minus zeta square under the square root times t. Now I'll remind you, if you watch the video which I given before, or if you read in the book, I don't know. So 1 minus zeta square under the square root, it's beta. And omega n times 1 minus zeta square under the square root, it's omega d, the damped frequency. So let's go back to our transfer function, that one. We'll put it in this form. So what do? I have, this is omega n square. So I multiplied by omega n square. I divided by omega n square. I have 10 from there. So I'll have 1 over 50, don't forget it. Of course, beta equal 1 over this, which we talked about. We have zeta omega n from here equal to 10, is 20 divided by 2, so it will be 10. We get zeta equal 10 over omega n, and it will be equal to 10 over 10 square root of 5. And we get zeta equal 0.447. So beta will be, using this expression, it will be 0.894. 1 over beta equal 1.12. Okay? And omega n, omega equals square root of 500, and it's equal 22.361 rad over second. So now I write the expression for the response. Vc of t equal 1.12, and this is omega n. This is 1 over 50, which we left from here. E2 minus 10t, zeta omega n 10, sine 20, which is 20 is the omega d. Now, if you watch this response, it's a funny, it's not a step response like. So it's, if we substitute for 0, this will be 0. So the system will have 0 value at t equal to 0. And if we put t equal to infinity, this will be 0, the e2 minus 10t. So it will be 0. It looks like an impulse response. Why it looks like that? I'll draw it for you maybe here, although it's small. So it will go like that. It will have, then it will go to 0. Okay? This is t. This is Vc of t. It's small, but it's clear. So it looks like an impulse response. Why the voltage on the capacitor became equal to 0 after a long time? Because I'll remind you of the shape of the circuit. You see, Vc, you remember that Vc, when it's charged up to a maximum value, it will act like an open circuit. But because we have an inductor here, this, after a long time, this will act as short circuit, and the voltage here is equal to 0. So this will, voltage will equal to 0 as t goes to infinity. Okay? This is question number 12. Now, if we go to question number 20. The question, he give us a few transfer function, A, B, C, and he want to find a typical question, as we say, zeta, omega n, settling time, peak time, rise time, and percent overshoot. Okay, so I'll do this for A, and those two is similar. Now, as I said, we solve A. So let's say zeta 2 zeta omega n equal to 3 from this one. Okay, and so zeta omega n equal 1.5. Then we have settling time equal 4 divided by 1.5 zeta omega n. So TS equal 2.67, of course, in second. Now omega n, you remember this is 16. So omega n equal to Jethro 16, which is 4. So zeta omega n equal to 1.5. Then zeta equal 1.5 divided by omega n. So it will equal 1.5 divided by 4. Okay, and equal 0.375. So this is zeta equal 3.75, and we found settling time equal this. So we need to find omega d. Of course, from here we can find percent overshoot. It's at the bottom of the paper. And now we have omega d equal omega n times 1 minus zeta square under the square root. And here is the calculation. We find that omega d equal 3.74. Remember, as I told you before, omega n is 4, omega d 3.7, and I told you that omega d is always smaller than omega n. Okay? Of course, rad على second. Okay? Now, omega d equal 3.71, then Tp equal pi over 3.71, and it's equal 0.847. Again, Tp is much smaller than settling time. Percent overshoot, as we have zeta, then we can find it from this expression, times 100, and it's equal 28.06%. And this question, this type of question, I call it a forward, easy forward question. So if you study the material, then you can solve this easily, because it's only you apply the rules and expression that you have. Okay. Now I told you about rise time, and it's have a long expression to solve. The expression given in your book is that one, omega n tr equal to this expression, 1.76 zeta cube minus 0.417 zeta square plus 1.039 zeta plus 1. From here, you know omega n, you can solve. You can find tr equal 0.356 second. And I gave you an expression. You can see that it's this is an approximation for it's the tangent to the curve in the book. And I gave you an expression, another one, which is tr equal 1.8 over omega n. But there is a difference. This is 0.356, while this 0.45. But it's easy to use. So we'll tell you later that which one to use, because this is it takes a bit of calculation. So if you try to solve B and C, it's similar to A, so we don't need to repeat the same question. Now let's go into question 26 in your book. Okay, it's giving you the system. He's choosing the input T here and theta here, and the output here, theta 2. He wants, of course, the transfer function theta 2 to t. Okay, theta 2 to t. No need to t1, theta 2 to t. So we need to find this. Let's say equal what? And B, this is A. B, he wants percent overshoot, settling time, and peak time. So you can see that this is, we took a question which is electrical, which is that the one we solved with the node equation, and now we have a mechanical system, which those both systems are taken in chapter 2. So now we apply and we use this model again, so that we apply them in the to find what you required in chapter 4. So first of all, we have to write the equation for both. I'll write the equation directly into Laplace. So we'll say this j s square plus 2.24 for this one times s, theta 1, that's due to theta 1, minus, let me use this pen, maybe better, okay, minus 2.24 theta 2, this 2.24 due to theta 2 from the theta 2 equal to t of s. This is one equation. Now if we come to equation due to this is due to this theta, okay? Now we say minus 2.24 due to theta 1, this one, and plus 2.24 s plus 1.53, this is due to theta 2 s, and this 1.53 due to theta 2, and here is theta 2. So I have equal to 0, of course. I don't have a torque here. So I have two equations in theta 1 and theta 2. We solve. Of course, you remember Cramer rule. So we solve by Cramer rules. So we say theta 2 equal we call this the A matrix, the determinant, which is delta, the one in the denominator. This is equal to delta equal this one, right? Or that one, the one with the negative, and this one with the negative here, and 2.24s here plus 1.53. So you get the determinant of this. So this is determinant due to, what did we do? We kept those due to theta 1, and we removed those due to theta 2, and we put the torque here t and 0. Calculate determinant this by this minus this by this. So it will be, it should be minus? No, because I opened all this. Okay. This will be this by this equal to 0. And this, after a few manipulation, this will be equal to, this is transfer function. So now if we have theta 2 over t of s, it will equal 0.935. This comes because I have here, you see, I have this coefficient. You have to get rid of it. That's why it's changed here. You have to make this equal to 1. Otherwise, you will have all your calculation equal, it will be wrong. So theta of 2 by t of s equal 0.935 over this denominator. So now from the denominator, you know that this is omega n squared. This is 2 zeta omega n, y omega n squared. So omega n equal 1.1954, this one. 2 zeta omega n, this one, 0.6835. ينتج عندنا zeta omega n divide by 2, it will be 0.342. So the settling time equal 4 divided by 0.342, and settling time will be 11.704. This is an indication, long settling time indication of zeta is small, because system will keep oscillating, so it will take a long time to settle down to steady state value. Okay, so and percent overshoot, you know, from using this e to minus zeta pi over 1 minus zeta square تحت الجذر في 100. هاي تستعملها, you can find the percent overshoot. So what did we do? We have to write two equations in theta 1 and theta 2. We find the transfer function theta 2 to t by Cramer rule, and once we find the transfer function, we can find the characteristic very easily. So this is the question 26 in your book. Now, let's go to a different style of questions. Now, we have 29, it's have 3 parts. I'll solve you 2 parts, and the third part is similar to the second. So consider the step response given, find the transfer function of each response. They are 3. I'll solve for you 2 of them, 1 first order and 1 second order. The third one is similar to the second one. Okay, now he's given us this response. Of course, you remember I told you before that the typical first order system transfer function is equal like that, k over s plus a. This k and a, they don't always equal, okay? But the pole is that one, minus a. So we'll want to find, he wants us to find the transfer function of the system. He's given us this response. So we need to find k and a. How we go about that? First of all, from the figure here, it's clear. From the figure, we see that the C steady state is equal to 2, okay? Now, from the transfer function, we go to final value theorem. We say that C steady state equal limit as s goes to 0, s c of s, and equal limit as s goes to 0, s, k, and r is taken as a step, of course, because this is step response. So I put 1 over s for r, so it's equal k over s times s plus a. We omit this by this, so substitute for s equal to 0. So the C steady state will equal k over a. So I'll have C steady state k over a equal to 2 from the figure. So I found an equation in k and a equal to 2. So I need another equation so that I can find k and a. You need 2 equations to find 2 parameters. Now, from figure, this is our final value. And you remember that the time constant of the system, which is related 1 over this, the time constant. So 0.63 of the final value is equal the location of the output at which the system يقطع 1 time constant. So I'll take the time constant, the steady state value 2. I multiply it by 0.632. This, you remember, time constant, the time at C equal 0.632 C steady state. So it's 2 times 0.632 is equal 1.264. I'll go on the figure. I'll put 126. Of course, it's difficult to show you exact numbers because they are just figures. So it's difficult. Just show you the procedure. So I get 1264. I'll go and put here 1.264. I'll go here, put it down. And actually, this is 0.244. It's too near to 0.05, so maybe you can argue this is not 0.244, but it's just a figure. I'm showing you the procedure. So this is 0.0244. This is our time constant. Now A, the root or the pole, is equal 1 over the time constant. So I say that A equal 1 over TC and equal 1 over 0.0244. So TC 0.0244. A equal 40.984. So I find A, this is 2. Now K equal 2 times A, so I'll say K equal 2A. I'll substitute for A here. I get K equal 81.967. So I got A, which is 40.984, and I get K, so I substitute for my transfer function, which I found from the figure. G of S equal 81.964 over S plus 40.984, and this part, which is A, is done. I'll do you in the next video. I'll do the one for second order system. Okay, thank you.